This is Geometry A, Unit 6, Congruent Triangles, Lesson 5, Isosceles and Equilateral Triangles. So we're going to look at particularly isosceles and equilateral triangles. But first we need to define our terms. Isosceles. It's a fancy sounding word. It's kind of fun to say, isosceles. You need to practice spelling it a couple times. It's a triangle with two congruent sides. Isosceles, two congruent sides. Let me draw an isosceles triangle here. I'll draw it here. There's our what we call the vertex angle and the base angle, which is 4 out here. There we go. So we have some words to define. I've already used a couple of them here without defining them. Okay, so we have two sides that are the same. And the third side can be the same, which would make it equilateral, but it doesn't have to be. So an equilateral triangle also is isosceles. Okay, so in isosceles triangle we have two sides that are the same. Two sides that are the same. And we are going to prove something called the isosceles triangle theorem, which says something about the base angles. Okay, but we need some words here. The angle that is formed by the two congruent sides is called the vertex angle. The sides that are congruent are called legs. The side that is not congruent, or the third remaining side, is called the base. And the angles that adjoin the base are called base angles. Base angle, base angle. Okay, so some words that you need to know. Okay, let's do a proof here. We're going to do a proof, and I'm going to do a proof by drawing a line right down the middle. Now there's a couple of ways I can do this proof, but I'm going to do it this way. I'm going to draw a line segment connecting the vertex angle to the midpoint of the opposite side, so it divides the base exactly in half. Okay, and we haven't made any statements about angles other than that. Okay. All right, so here's what I'm going to prove. Okay, given, let's label some sides here, A, B, C, and D. Given AB is congruent to CB, okay, and given AD is congruent to segment CD, prove, and here's what I'm going to prove. I'm going to prove the angles, the base angles, are congruent. Angle A is congruent to angle C. Okay, so let's start with our proof here. We're going to start with our statement and our rules. First statement is usually the given, and I'm not going to break that rule here. AB is congruent to CB, and AD is congruent to CD. How do we know? Statement 1 has rule 1, which is given. The only time we can assume in a proof. Okay, and we're going to end with, and I don't know what step number it is, angle A is congruent to angle C. That's when we know we're done. Okay, let's go ahead and do it here. Do you see any Siamese twins or bow ties? Any shared sides or any vertical angles? And there is a shared side right here. So I'm going to make this statement here. 2, BD is congruent to itself. BD. What do we call the rule that says anything is congruent to itself? We call it the reflexive property. Not reflective, but reflexive. It has more to do with reflexes, like when the doctor hits your knee with a rubber mallet. Reflexive property. It's reactive. Anything's congruent to itself. All right, so let's see what we've got here. I've got a side congruent to a side. I've got a side congruent to a side. I've got a side congruent to a side. Are they all in the proof? Side, side, side. The triangles are congruent. So I can say step 3, triangle ABD is congruent to triangle. A goes with C, B goes with B, and D goes with D. And they are congruent by side, side, side. Now that they're congruent, we know that congruent means all the corresponding parts are congruent. So I'm going to bring this in here. Angle A is congruent to angle C since corresponding parts of congruent triangles are congruent. Okay, so QED quad erat demonstrandum. I said what I was going to prove, and I proved it. Okay, so let's explore what that means. Okay, what does that mean in a practical sense? Okay, because we can solve all kinds of problems using this rule. And forgive me for sketching quickly. I'm going to save some time here. If I have two congruent sides, and I know one of the angles, let's say I know this angle is 20 degrees. I happen to know the other two angles are the same. Pair that with the idea that the angles of any triangle add to 180, and I can write this equation: x plus 20 equals 180. Subtract 20 and add x plus x to get 2x. We get 2x equals 160. Divide 2 and x equals 80. So the remaining angle must be 80. Okay. But likewise, similar problem. Let's say we know this angle is 70 degrees. Okay, and we want to know this angle here. Well, the base angle, and we know these are the isosceles. These two sides are the same. We know then this angle is 70, and 70 plus x equals 180. Okay, 70 and 70 is 140. Subtract 40, and x is 40 degrees. Okay, 40 degrees. So you can use this to find missing angles. And also, we can extend this to equilateral triangles. If a triangle is equilateral, that means all three sides are the same. Okay? Well, think about it this way. If all three angles are the same, then that means, if I divide it this way, this angle is congruent to this angle. But if I divide it this way, that means this angle is congruent to this angle. So that means this is kind of a corollary to the isosceles triangle theorem. All angles in an equilateral triangle are congruent. Moreover, we can be even more specific than that. They're all the same, so call them x. That means 3 x's must equal 180. Divide by 3, and each angle must be 60 degrees. So every angle of an equilateral triangle is 60 degrees without fail, always. All right. So that's the isosceles triangle theorem.